the resources that you need for this session, I've got this just 2-page PDF, like I had a 1-page PDF this morning that we were just going to work through. And if you can stop and ask me questions whenever you want to, and I'll try and keep an eye on the chat, but if I'm missing something, you might need to unmute and speak. So what I'm going to do today is run you through Meta Essentials. As Sarah said before, this is like the big beginner session where we're working off free Excel-based software, Meta Essentials, that you can download and use to analyze different kinds of effect sizes. The example I have that this refers to is worksheet, is the correlation coefficient. It's the same example data set I talked about this morning, but I've also got an example data set that if there's time I'll go through. I think it's opened up here. This is one of her meta-analyses that we're doing together. That's for a comparison of means between two groups. So what I'd like everyone to do, if they haven't already, is go to Meta Essentials and download the Excel sheets. So Meta Essentials, if you're just getting into meta-analysis, or if you're working with maybe a student group that doesn't have any background in meta-analysis, it's such a good tool because it's free and it's very easy to use. You're basically just pasting things into Excel. So we need to download sheets here. Hopefully everyone's done that. I'll just do it now so I can gauge how long it takes to do. So this is what it should give you when you download the Meta Essentials workbooks. It'll give you 7 Excel spreadsheets and some manuals. And again, if you're new to meta-analysis, these manuals are great. How to interpret your results. And then this user manual has some more detail about how to interpret your results. So I've downloaded them earlier, so hopefully you've also downloaded them and can put them somewhere. Let's go back to the sheets. So I'm going to get you to use the data file from the Open Science Framework. So if you've got this web sheet, you should have this, I hope. You can just click download. And the instruction manuals. And I'll talk about the positives of Meta Essentials. There's 2 big positives. The first is that it's free. Unlike Covidence or unlike CMA, I mean, R is free too, but with R, it's not great for beginners, whereas this is. So if there's something that you wanted to do, but you've never done a meta-analysis before, this is a really great place to start because you don't have to invest a lot of money or time into just starting to do it. Now, the negatives are that there's only a certain number of things you can do. So Kip is talking about doing meta-analyses in R, which has several advantages. So with Meta Essentials, you cannot look at within study effects, only between study effects. You need to use the R package RoboMeta or similar stuff to do this more complicated analysis involving multi-level modelling if you want to look at within study effects. And by that, I mean, if, for example, in one of Sarah's meta-analyses, every paper measures 2 parts of the personality trait narcissism, grandiose narcissism and vulnerable narcissism. And you want to look at differences in how those 2 traits relate to something, relationship quality maybe. That's a within study comparison because every study has those 2 things and you can't technically do it. You can only look at differences between studies. Meta-analysis cannot look at multiple moderators in the same meta-regression. You can only look at one moderator at a time. And the graphics, like the pictures that you get out of them, they're not especially sophisticated. But yeah, great starting point. So I'm going to start by just going through the meta-analysis of the systematic review that I did this morning, which is published in this paper. It's pretty simple. So what I'll get you to do first, this meta-analysis, it asks the basic research question is, do emotional intelligence abilities relate to positive affect? And I searched all this stuff and coded it in a code book. And now we're going to put data from that code book into Meta Essentials. So I'm going to just open Meta Essentials from my SIS review workshop. So you should have downloaded this. And what we need to open is the correlational data sheet. So correlational data 1.5. And this is what it looks like. So the input tab here is where you paste in your correlation and your N here. And then it will give you the results of your meta-analysis. And the way that Meta Essentials is set up, it's started like you've got some like dummy data in there. So if everyone's with me, what we're going to use this data. So there's a link to the data. Oops. A link to the data here. And this is the meta-analysis that I talked about this morning for those who were there. So it's got the paper description, which I've got as author and year, and then all the other fields that I coded. The first and last author coded those, me and Kirill. So if I go back into the worksheet, what we're going to do first is just basically input the effects and the N and the study name. So there's my data. There's Meta Essentials. You can see it really is great for beginners because you just paste stuff in. So the first thing I'm going to do is the way I've set up my data sheet is this is the effect here for the correlation between emotional intelligence and total scores in emotional intelligence and positive affect. So I only want to enter those. So I'm just going to remove the blanks. Now, the way that I've set up my data, I had two effects here for this Dong et al. Paper that were from the same sample. So you can't enter those. You can't enter two effects from the same sample in a single meta-analysis. There's various things you can do when that happens. You can either pick one for some theoretical reason, or you can take an aggregate of the two. So what I did up here is take an aggregate of the two. So I'm just going to right-click there. I'm going to hide those. So these are the studies where there is an effect size for emotional intelligence total score with positive affect. So I'll copy the study name in there. And I only have 11 papers, so I'm going to delete all the data from 12. So the other thing to know about Meta Essentials is that when you first paste something in, it will calculate a lot of things on every other page. So it's a little blue thing that's going on for a while. So the correlation is here. This is my effect size. I'm going to paste it in. And the number of subjects is here. And I'm going to paste it in. Now, I'm going to leave this subgroup and moderator as it is for a while. We're going to come back to them later. Is everybody with me? Tell me if I'm going too fast or too slow, because I'm hoping you can all follow along. So this is where we're at in the worksheet. Now we're up to interpreting the output. So here we are, interpreting the output. So we've got this input tab, and I've just input these 11 studies. You can see that when there's sufficient data, when there's, oh God, what is that? What's it done now? When there's sufficient data to calculate an effect size, then Meta Essentials will automatically change this to yes. So the most basic thing that you can get out of a meta-analysis is the average effect. That's really what you want. When you ask a very specific question, does thing A relate to thing B? What you want to know is the size, direction, and significance of the effect. And that is this right here. This is not very impressive in this particular example. The correlation between these two things, emotional intelligence and positive affect, is 0.04. So when we're interpreting the effect size there, we'd use usually standard heuristics of Cohen. So for a correlation coefficient, correlation of 0.10 is small, 0.3 is medium, and 0.5 is large. So this is like smaller than small. It's positive, but it's really small. This gives us our confidence interval around the effect size. So this correlation is the sample weighted estimate for the correlation coefficient. It means that if we consider all of the data from these 11 studies together, our best estimate for the relationship between the two things is 0.04. Not very big. So I'm just going to move this here because I've got these definitions here. So the correlation is the sample weighted effect size. So a correlation itself is a standardized effect size because it doesn't depend on the units of measurement. It's always between -1 and 1. So you can interpret values of 0.1, 0.3 and 0.5 as small, medium and large, no matter what the scale of the original variables are. So when you're doing a meta-analysis, you need to enter only standardized effect sizes. And in this case, it's correlation coefficient. So it gives you a confidence interval around that correlation coefficient. You'd interpret it the way you interpret any confidence interval. If it does not contain 0, the results are significant. This does contain 0, so there is no significant relationship between ability, emotional intelligence, and positive affect here. Meta Essentials also gives you what they call a prediction interval. Sarah, you're going to put this recording online later, right? Is that
That's correct? Yeah.
So the prediction interval is something I honestly haven't seen outside of Meta Essentials, but this is what it means. It's the true value of the effect will fall in this prediction interval 95% of the time. So this is not, at least in my subdiscipline, a standard thing to report. This is though, this is critical. The correlation, the confidence interval, and the Z value and the P value related to the correlation, the sample rate effect size, which here is a correlation. So it's conventionally we use the two-tailed p-value. It doesn't even matter because neither of them are less than 0.05. So this is really not a very exciting result. Across all of the 11 studies, we have a total sample of 1895. So this is what we're interpreting here. We get a graph here. This is called a forest plot. This graph represents each study is represented here as one line. It's these studies here represented as one line, where the size of this circle represents how large the sample is. And this is the 95% confidence interval. This down the bottom here is the combined effect size. So this is the 0.04. And you can see the confidence interval as well as the prediction interval. Now, personally, if I was going to report this anyway, I'd probably take the prediction interval out because I haven't seen it outside of Meta Essentials and I think it confuses people. So what I'm going to do is just click on it and then click delete. So this has also, this line usually would be in 0. I don't know why it wasn't there. So just to illustrate like how many effects are significant across all the studies and with the total. So we would normally, you know, we could, if we're writing a paper, just take this graphic and it will become, you know, figure 1. Oh, look, I was excited about their project management slides before. Now you've all seen, and we paste that in there. Here, Meta Essentials. So this is the forest plot. I'm going to talk about a few other things on this page. The output on the heterogeneity of the effect. So what we see here is not very exciting results. What we see here is that the results are all quite different across the different studies, that if they were all very close to this value, then we would have low heterogeneity, we would have homogeneity, meaning the results of each study are all fairly similar. But it's all very well to eyeball it, but what you want to know a lot of the time is like some sort of estimate, like how different are these results from each other for each of these studies, represented here with a confidence interval. Are we confident that actually that these estimates, if each of these 11 studies is an estimate of the effect, were they all taken from the same population? Are they all randomly drawn estimates of the effect? Or is there something that means they're taken from different populations? So if there is high heterogeneity, we would think that these different effects might be taken from different populations of interest. So here's the output, other than just eyeballing it and going, oh, look, they all look like they're kind of different. Here's the output we would use to interpret the heterogeneity of the effect. So down here, we have Cochrane's Q. So Cochrane's Q is an indicator of the variability of effects across studies. As I'm mentioning here, if it's significant, there's more variability than would be expected by chance if all effects across these 11 studies were drawn from the same population. So we need to know it's not the absolute value of Q that matters, it's the p-value. Is it significant? It's actually not here, but it's close. If Q is significant, there's more variability than would be expected if all effects were drawn from the population. The other thing that we would normally report here is this I-squared. So the I-squared is the percentage of the observed variance representing real differences in the effect size. So these results might be fluctuating just randomly due to random error, or they might be fluctuating because there's some source, some variable, some reason that's making some of them higher than the others. Something about those samples, something about the measure that was used, something about the country that it came from, something like that. So if I-squared is high, and what is high? How long is a piece of string? Some people suggest that high is above 25%. This suggests that there are moderators of the effect, the things that I was talking about before. Things like, is it different for maybe student samples versus other samples? Maybe there's different effect in some countries than others, things like this. If I-squared is above 25%, there might be moderators, and moderation analysis should be conducted. I think I already talked about the forest plot, but there it is illustrated. So one of the things that people will talk about when they do a meta-analysis is whether they do fixed effects versus random effects. You almost always want to do random effects. If you do fixed effects, what you're effectively saying is that the effect is the same for, like, there's no other sources of variance except for the thing that you're talking about. Here, the only source of variance would be emotional intelligence relating to positive affect. The extent to which that's associated is the only source of variance. That's almost never true. So Meta Essentials suggests that, or by default, has this set to random effects, and we're going to keep it on the random effects. If the I-squared was super duper low, was 0, then maybe we would fix it to fix effects. The reviewers made me do that actually for one of the analyses, but it's usually a pointless thing to do, because if you really do have homogeneity in your data, then fixed effects and random effects will give you the same. They'll give you the same answer. They'll give you the same estimate. So this is like the most important result you get. In my disciplinary area, it's not, you don't always need to have the forest plot. My understanding is that in some disciplinary areas, especially in health-related fields, it's absolutely critical that you have the forest plot. This is like the main thing that people would look at in a meta-analysis. This is the main thing that you would put on your PowerPoint or whatever that's giving a presentation on your meta-analysis. So if you wanted to change anything about this, I mean, it's in Excel, so I could just edit it like I would always edit Excel. I could make them orange and things like that. So you can do things like that to make it look however you want it to look. You can also here sort the order of studies in your forest plot. And I think at the moment it's sort of by entry number, study name. I think they're already in alphabetical order, but I could sort by study name. You might want to sort by low to high sample size to see if anything's going on there, because if all the low sample sizes had no effect, you might conclude that actually that's because they're underpowered. But no, the two lowest sample sizes are quite far in the opposite direction, so that's not the case. You might want to sort by the effect size. There's not a strong reason to do that, but in some areas, sorting by the effect size, it might be immediately obvious that all the high effect sizes are the same author or from the same country if you do that. So this is at a very basic level, what you get out of the Meta Essentials first page. So does anyone have any questions before I go on to talk about publication bias?
I do really quickly, but I'm not sure whether my sound's going to cut out. Hang on, let me just put my speakers back in. Sorry, this might be a really obvious question. If you were looking at the moment, I'm thinking about doing a meta-analysis looking at effects of parenting interventions for adolescents. And there are particular skills that I want to look at for efficacy. Would I need to use a different Excel sheet for each of these meta essentials for each of those specific skills? Or is there a way that I can do it all in one go?
So just slightly complicated answer. I mean, firstly, I think you probably, would that be usually stuff where it's pre-post or something? So you'd be looking at a different one. Where is it?
Very, very possibly.
Dependent groups, I think, because you've got the same people. So wouldn't it probably, I don't know what research is out there, but I'm assuming it would be dependent groups. I'm also assuming that you'd have a lot of within study effects that have, so, you know, some programs contain this and some programs contain that. And I'm not sure if that would be within study or between study effects. So I guess in the simplest answer would be, yeah, you've got to, if you've got multiple DVs you want to look at, which most people do, I do as well, I'm just talking about one here for the sake of the workshop, then yeah, you do loads of them.
Cool.
Let me just check. I don't know if I kept it in a good, I did the effect of emotional intelligence on positive affect and on negative affect, and for the 4 different kinds of emotional intelligence. So I ran 10 of them in 10 different Excel sheets.
Great, thank you.
Any other questions? So I'll go on then to show you what information, or at least some basic information that you can get out of Meta Essentials for publication bias. So publication bias is a thing that occurs in our publish or perish environment, where people, if they don't find a significant result, they don't publish it. So that when you're looking at the published literature, you'll find a big gap. You'll find like it's biased towards only reporting things where there was a significant effect. So if there's a file drawer effect, if there is a whole bunch of people doing research but finding nothing worked and just leaving it in the file drawer, then you'll have publication bias. The things that are published will be an overestimate of how large this effect is. And this is a big problem. It's one of the reasons why people try desperately to get unpublished data, of which theses are often a good source, as well as writing to people for their unpublished data. But we want to know in any meta-analysis, to what extent is this a problem? To what extent do we think there's a whole bunch of things in the file drawer that might push down the size of the effect? In this particular meta-analysis, I doubt it's going to be a problem because the effect is basically 0. But I'll show you what it looks like. So we're going to go to the publication bias analysis tab, just here. So I'll point out, so I said before, if you recall, that we always pick a random effects model, because even if even if it is fixed effect, it should converge. Whereas if you have heterogeneity in your data that use fixed effects, then it's not, it will produce an erroneous estimate. However, for publication bias, you'll notice that Meta Essentials, that Meta Essentials default is a fixed effect. And this is because many of the publication bias metrics assume that you have fixed effects, that they're based on an assumption that they're fixed effects. So what this means in practice is that if you think that, if you want to check for publication bias, it's best to do so, probably getting ahead of myself actually. One source of heterogeneity is moderators, like I was saying before, like maybe this is, maybe some of the variability between studies can be explained by the fact that some are from American teams and some are from Australian teams. And if we account for that, if we have separate estimates for American and Australian teams, and that actually is the source of heterogeneity, then within each of those groups, the American studies and the Australian studies, we've got lower heterogeneity and it's more likely to be accurately explained in a fixed effects model. So applying this to publication bias, it means that if you're trying to check for publication bias, you want to do it in whatever bit of your data and analysis has the least least heterogeneity. So you'd be wanting to look at it for, in the example, separately for the American studies and the Australian studies. So that was all very long-winded, but that's why this is set by default to fixed effects. Although I think in practice, a lot of people ignore that and just go, okay, I did a random effects model. So obviously I should be checking for publication bias based on the model that I actually did. So the most conventional thing to check, or the first thing most people think of, is a funnel plot. So this is what a funnel plot looks like. What you really want to check is whether these, if I had actually any effect, the dots would be like on these lines or on the outside of these lines. And in this case, there was pretty much no effect. What you want to check is whether it's symmetrical. So here's the effect here, which is tiny, it's 0.04. Are there more studies that find the effect or more studies that don't? And are they equally clustered around that effect size? Are they normally distributed, these different estimates from each study, around the average effect size? So basically, if you fold it in half, does it look kind of the same? Like you could visually inspect it, or you could look at open this. You can look at it visually, or you can see if Eggers G, the intercept, after I type that, the intercept from Eggers regression, this is a measure of whether the funnel plot is asymmetric. So if Eggers G, which is here, is significant, that's an indication that you've got publication bias. Here we can see that the confidence interval is truly enormous. It goes from -3 to 4. This is the t-test and the p-value associated with that. So it's not significant. The Eggers test is not significant. So we do not have significant publication bias. It's pretty unlikely we'd have significant publication bias if we had pretty much no effect, because that's why we. So the other thing, this is not shown here, but I found an example that did show, here's an example of what it might look like the funnel plot if there was publication bias. So if you see there's these two orange circles here, this is, I got to this from a different example by using the trim and fill procedure. So it's this is down here. So it's on by default. So that means that if you think that two studies have been tucked away, but because the distribution of effects around the aggregated effect that you've just got to meta-analysis, the two studies have been unpublished but probably exist somewhere, because we assume that if it's just random error, everything will be evenly distributed around the real effect. Then the imputed data points, the missing studies, come up as orange circles. So that's an example here of two missing studies where we get an estimate of publication bias. So what you would normally expect if the file draw effect was real is that the missing studies would be things that show an effect that is sort of that is close to zero or in the non-hypothesized direction. Again, this isn't the greatest example, but this is real data, and it was the only one I could find that showed the publication bias, because it's suggesting that there's two studies out there that have found a large positive effect, as we would expect, but that they haven't been published. So if you were to correct in this case for publication bias, you can see what would happen. The original estimate, this green line, would get like, the original estimate would change. So here, what have we got? We've got the adjusted estimate in red. So in my example, the adjusted estimates actually got pushed up a bit. So trim and fill is what you would normally do to avoid reporting an erroneously high result that's due to the file draw effect. But you've got to be careful. I think what I'm illustrating with my thing, you've got to be careful that the trim and fill has actually identified a file draw effect. Because here it hasn't. It's very unlikely that people are sitting on data showing like a really big finding and not publishing it. Someone's asked in the chat, is meta-analysis still publishable if it shows publication bias? Absolutely. Publication bias is a common thing. If you did not even look for it though and just assumed it wasn't there, like reviewers would criticize you. So it's important to consider publication bias. Firstly, by trying in your search process to get as many sources of unpublished data as possible. And second, by checking for publication bias. Okay, so here we are. This example is not symmetrical. A trim and fill procedure shows two imputed circles, and Meta Essentials has adjusted the effect. So if you did have publication bias and you wanted a true estimate of the effect, you would adjust it to account for publication bias. And you would adjust it usually with this trim and fill procedure. So where you're imputing the studies, well, basically the studies that you think are missing that have been left in the file drawer. These are the most common things that people do to look at publication biases. Meta Essentials also reports a lot of other ones. I wasn't going to go through these now because they're all described in so you just downloaded this. They're all described in these manuals, and I thought I'd just go through the common one. But to get to them, you can see they have this hiding and unhiding of the Excel columns. So you can look at the standardized residuals. So I think you're in the wrong room if you're asking about our person in the chat. In the standardized residuals, you want these to be like relatively normal. And this is the Galbraith plot. You want everything to be between the two lines. And there's some other things here. You can look at all those things, the fail-safe end. So these are like the main things that you want to get out of a meta-analysis. Firstly, the actual basic output. Secondly, the forest plot. And thirdly, the publication bias analysis. So I'm going to show you quickly, I think, how I reported that in the paper where I did that. And then I'm going to go on to show how you would look at separate groups analysis and moderators. Is this size visible to everyone? Or should I download it and make it big?
I can see it okay, but I have a huge screen.
I finally got my screen back today. So good. So yeah, this is how I reported the meta-analysis. So we've just done this meta-analysis. Unfortunately, there we got the same result with that it was 0.04. Now, what I did was something that is common in OB and organizational psychology subdisciplines, is to correct every estimate of the correlation coefficient for unreliability first, and that would be called rho. But if we didn't do that, we just report the K, that's the number of effects, which is 11. So that's here. This is your K and your N. 11 is your K, 1895 is your N. The effects, that's here. And now I reported all this other stuff for the corrected correlation, but if you're not going to correct it, if you're not going to correct the correlation, you'd report all this just for your R. So you would report the 95% CI for R, or rho is the corrected one. So it contains 0. This is the Z value. It doesn't have any little stars because it's greater than 0.05. This is Cochrane's Q and the p-value associated with it. And this is the I squared. So as I said earlier, I did 10 of these. So these are the 10 and I put them in a table. And that's like, there's various complexities with which you can get into in meta-analysis, but this is a relatively simple one, and that's the results of it. Would it be helpful if I went up and showed you the text as well as the table enough? Find the text. So this, if you wanted to look later, there's also all this stuff about the search strategy and the Prisma chart and the effect sizes. And so this is how I described the analysis. This is in the statistical analyses part of the method section. Random effects, meta-analyses are conducted using meta-essentials, table 1. And this is my statement, which is not very sophisticated, but reviewers accepted it. Publication bias, which I just talked about, was assessed by visual inspection of funnel plots. All but 2 plots were symmetrical. This one, where 3 studies were missing from the right-hand side, and this one, where 2 studies were missing from the right-hand side. So this is what I was saying before, in that my results are a bit weird if we're talking about the file drawer effect. That is, a trim and fill procedure would increase the hypothesized effect and produce a larger estimate. I thought that was very unlikely, so I didn't correct for it. But if you did find that evidence for a file drawer effect where people were not publishing significant or large effects, you probably would want to correct for it and then point out what you did here. And usually I didn't do it, but it's slightly weird not to report Eggers G or something like that. So I had hypotheses related to the meta-analysis, so I reported them here. So that's it really. Very, very short. So I'm going to go back to our demonstration of meta essentials and talk about tests for moderators and subgroup analyses. So if you have a large amount of heterogeneity in your data, it's highly likely that there are moderators that you're someone's asked, are these forest plot and other plots Excel generated? Yeah, everything, Meta Essentials is just Excel. It's just an Excel workbook someone developed with a lot of formulas in the Excel sheets. They do, I mean, you can, if you don't have Excel, it can run in a couple of other things, but that's basically what they are. So going back to the discussion of moderators, if your effect is heterogeneous, it may indicate that you've got moderators. So I'm going to test for this data set, one of the very common moderators, which is that is the percentage of females in each sample, is that something that moderates effects? So it's actually relatively common in my research area that you get stronger effects of emotional intelligence for men. So it might be reasonable to check that. So I'm going to paste the percentage female into the moderator column. And then I'm going to have a look at the moderator analysis. So I'm going to change this to random effects because that's what we've actually got. So this moderator analysis in Meta Essentials is a meta regression. So we've put all of the studies, the correlation plotted against the moderator, and we've run a regression on this sample size of 11. So we've, regressed. We're predicting the correlation from the moderator. And if that prediction is large and significant, then we've got an indicator that the moderator is accounting for the variability in our effect size. So that's literally what we're doing. We're saying the IV is the moderator, in this case, the percentage female, and the DV is the correlation. And it looks like as we increase the proportion of females, we're getting stronger effects. We can have a look at the effect size for that, which is actually really quite big. A standardized regression coefficient of 0.5, which is totally not in line with what I just said about effects normally being bigger for males. It's not significant. The p-value is 0.078. So we would conclude that it's not a significant moderator, the percentage of females in the sample. We could also see if age is a significant moderator. the mean age of the sample. And if I wanted to, I could, you know, in the standard way that you did in Excel, like change the axis to have more meaningful label there. So this is also not significant. What some people do, and this is more relevant for some kinds of research than others, I think they've even got a separate column for the year, but I could enter the year of publication, because sometimes it might be that there was like a new treatment that was available after some year, or people were getting better and getting more training at doing something. We think that the effect would be bigger for recent studies. So this is basically how moderator analysis is tested in meta-essentials. You have a meta-regression where the moderator predicts the effect size. You interpret that in the same way you would any regression. There's a standardized regression coefficient, and you check whether that's significantly different from 0, and it's not. So don't worry. We don't have any evidence that there is moderation here. But of course, we don't have, like with our 11 studies, we don't have a super large degree of power to determine whether there is in fact significant moderation. So going back for a moment to what I was saying up here about one of the limitations of meta-essentials is I might want to look at multiple moderators in the same meta-regression. Meta-essentials does not allow me to do that. There are many R packages that you can use for meta-analysis. Metaphor is one of them. Where you can look at multiple moderators in the same meta-regression. But you can't do that with meta-essentials. You have to look at them one at a time. So I'll go now to the next stage, which is to do subgroup analysis. So if you have multiple subgroups in your data, so the example I'm going to use is data collected in the USA versus elsewhere, but sometimes there's a really conceptually meaningful one that isn't really, like people have used one particular training type versus another, or one particular measurement instrument versus another, and you want to look at whether the effect is different for those different things. You might do subgroup analysis. So in this case, I was going to look at whether it was USA versus not. So I'm going to go into the input sheet and enter these as subgroups. So now go to subgroup analysis. We should have separate estimates for the USA and non-USA. So if I go here, we'll be able to see that. So this tells us for between group ratings, we're using random effects. For within subgroup ratings, we have a choice. We can say, or we can decide that we think actually all of the variation in all of the sources of heterogeneity is just this particular subgroup, and therefore within each subgroup we're going to do a fixed effects regression, which is usually somewhat unlikely, but I guess theoretically possible. Or we can say we're going to calculate heterogeneity separately for each subgroup, which usually is recommended, or based on effects as a whole. So what we've got here is the effect size for outside of the US is 0.09. And actually that confidence interval now does not include 0. For the US, the confidence interval is 0. Someone's asked me how many groups can you compare? I don't know what is the maximum number that this can take, but certainly more than 2. I haven't ever explored the maximum possible number. What you're usually really limited to in practice is if you're going to do separate meta-analyses within each group, so here the USA and non-USA, you want to, you don't want to have every group only has 1 or 2 things in it, where it's not really, there's not really reason to do meta-analysis. But this is kind of interesting to us, is that we got nothing in the USA, but we have this small positive effect in these studies outside of the USA. So I have no understanding of why that might be. If I had picked a theoretically meaningful moderator, maybe I would. But that's what this is telling us, is that there's an effect in the US, in the world, but not in the United States. So if we wanted to have a look visually at what this looks like, we can see that here's the studies for outside of the USA. None of them are really that impressive. The effect size is still small. And here's the studies within the USA. And here's the outside the USA example and aggregate estimate, and here's the within the USA aggregate estimate. So we might want that plot. We might, and if we've got a very large data set, which I've had in the other meta-analysis that have 5 different subgroups, you might want to have a graph that only has the subgroups. So this is also makes it kind of clear. You're like, oh, the USA is all over the place. So much heterogeneity. The other studies, the sample sizes are larger and there's less heterogeneity. This is a way of trying to figure out what's going on in the data. Now, one of the things that is slightly frustrating is that a lot of people want to use subgroup analysis to say, is this estimate, 0.09, significantly different to this estimate of 0? But subgroups analysis does not tell you that. It just tells you what the estimate is within each group, but not if they're significantly different from each other. If we wanted to know, now that we've done this, is USA versus not USA significantly different, we might enter it as a dichotomous moderator in order to determine, are they actually significantly different? So I'll just do that. Moderator analysis, and the graph is useless because our values are 0 and 1, and we go from 15 to 45. So how about go from 0 to 1 now? That would be better. from -1 to not a lot's going on there. And I think that's because in the USA, which I coded as 0, we've got a very large amount of heterogeneity. So that was it for the worksheet, but I also had another example that I could go through. It's of Sarah's data that looks not at correlations, but at mean differences. So I'm going to pause for a moment and sort of take 5 minutes for questions, and then I'm going to go on to show that example. All right, so it looks like there's not a lot of questions, or we've hit the point in the afternoon where everybody's just quite tired. So I'm just going to go on and show you this example of comparison of groups. So on the systematic review page on resources, I think it's actually for the morning session, but I'm just going to look at it now. So Sarah, this is like your data, although I like simplified it a bit for the purposes of teaching. So if I say anything is incorrect about it, you have to correct me.
I'm sure it's totally fine.
So what we have here was the research question of interest was when you are using a psychometric assessment of psychopathy and people are motivated to get a good score. So this could be in forensic applications where you're giving people a psychopathy assessment to determine are they eligible for parole or are they risk or whatever, or it could be for some sort of job application process where you're trying to make sure that you're not letting someone into a clinical psychology program if they have very high levels of psychopathy. I mean, there's various reasons you give people these under. And you want to compare what happens when you give people an assessment of psychopathy under standard conditions where you're reasonably sure they've been honest, and under some other condition where you're reasonably sure that there's motivation to get a particular score. So these are differences between groups. So where you have here in this Anderson et al. Paper, you've got 127 people who were given this psychopathy test under honest conditions, and 114 people who were then told, you should answer this, to make yourself look good, to make yourself get some sort of positive outcome from taking this test. So the question of interest here is how much do people change their scores when they want to look good? So I'm going to open now the Meta Essentials workbook, differences between independent groups for continuous data. So the groups are honest and fake good, and the continuous data is their psychopathy score. Okay, so this is the example of the example data in the Meta Essentials sheet for comparing differences between two groups. So you can see that this middle bit where you enter the sample size and the effect size is a little bit more complicated than it was for the correlation coefficient. This is because there's various different ways in which you can enter the effect size. You could enter, as in this hypothetical AAA study, the means of group 1 and group 2 and the standard deviations for group 1 and group 2. For everything, you've got to enter the N of group 1 and group 2. But you don't necessarily have to enter it to have sufficient information to get an effect size. You could have the means and the standard deviations. You could have the means and the pooled standard deviation across the two groups. You could have a mean difference and the standard deviation of the two groups, or the mean difference and the pooled standard deviation. You could have a t-value. You could have an f-value. You could have already calculated the effect size, either as Cohen's D or as Hedges G. They're very similar, but Hedges G, they're the fraction of a standard deviation by which groups differ, that Hedges G takes into account uneven sized groups. It does so in such a way that it's probably more accurate also if you have very small samples, as in this case. So it's a little bit more complicated to enter sufficient data to get an estimate, but I'm confident that we can do it. So we've got these studies, 11 of them again, lucky number 11. And I'm going to remove all the default data so I don't end up entering that by mistake. So if everyone's with me, we've got the sample size here and here for the two groups, honest and fake. So I'm going to enter that. Here I've got the mean scores for the two groups. So I'm going to enter that. Done something odd there, I've made a pasting error. And I've also got standard deviations for the two groups. I'm going to enter those. See, hopefully that is like, yes, there's now sufficient data for all these studies. You're now able to calculate an aggregate effect size. So if I go in here now, it's all very similar. We've got a forest plot. We've got an estimate of the effect size here. So this is Hedges G, which in this case is -0.67. So when I was talking about effect sizes with correlation coefficients, we generally, because Cohen said so in the 60s, think of values of 0.1 as small, 0.3 as medium, and 0.5 as large. But for Hedges G or Cohen's D, the fraction of a standard deviation that groups differ by, we have a different idea of what values mean small, medium, and large. 0.2 is small, 0.5 is medium, and 0.8 is large. So what we have here, if I was to interpret the effect size, is a moderate to large effect of differences between groups. And what they're doing, the way this is calculated, is it's mean 2 is when they're faking, when they're trying to look good. So the fact that scores go down when people are motivated to fake on psychopathy tests is what we would expect. They're decreasing their scores on these psychopathy tests by an average of 0.67 standard deviations. So as with the correlation coefficient, everything's kind of similar. You've got the effect size, the standard error, you've got the confidence interval, and you've got the prediction interval that is not used outside Meta-Essentials, so I usually ignore it. But I think there are some subdisciplines where that's a very useful thing to know. You've got the Z value and the P value. So the two-tailed P is, let's see actually what the exact value of this is. The P value is very small. We've got 11, K is 11, N is 2935. If we look at the estimates of heterogeneity, there is considerable heterogeneity. Our I-squared is 86% and Cochrane's Q is significant. So there's heterogeneity. So of course we should be using a random effects model. So if you are looking at differences between groups, you could pick either Cohen's D or Hedges G as your estimate of the effect. They're interpreted in the same way. Hedges G is like a little bit more sophisticated because it considers the relative size of the two groups in terms of how it calculates the pooled standard deviation. So I'll just stick with that. That was the default. I can sort the values by whatever I like again. Number of subjects, effect size, all this kind of thing. Look at effect size. Oh, maybe I'll look at sample size. I'll see, is it the smaller samples where that have like the smallest effects? Not really. Is there anything that here that can give me a bit of a clue if I look at it as to what the sources of heterogeneity are? Not really. Is there any publication bias? Ooh. So this again, this is telling us that maybe there are these studies missing because it's not symmetrically distributed. It doesn't actually change the effect size that much though. We've gone from a Hedges G to minus 0.32. And we've got some imputed studies there. And if we look at the Egger intercept, it is in fact significant. So what else are we going to look at? I think so if we looked at it this way, where we've entered the means and standard deviations, we've got that minus 0.67. I've calculated Cohen's D myself over here for each study. So if you look at my formula there, it's the mean 1 minus mean 2, and this is the formula for the pooled SD. I've also calculated Hedges G, which has a more complicated formula for the pooled SD. It's the difference in means divided by the pooled SD, standard deviation. This is complicated because it takes into account the size of the two different groups. But you can see they're extremely similar. If you've got large groups with very similar standard deviations, they're going to be the same. So what I might do now is, instead of entering the means and SDs, I could just directly enter Hedges G, and it should tell me I have sufficient data, except it didn't because I pasted the formulas in instead of the values. If we look at the forest plot, we can see again the Hedges G is 0.67. So it was negative 0.67 before. I think that's because I calculated it differently. I calculated it, how did I calculate it? As honest minus faith, mean 1 minus mean 2, which is not actually that intuitive, because usually when we look at the post-treatment or the second group minus mean 1, but look, it's given us the same thing. So this is the extent to which I was sort of had prepared to show you things in Meta Essentials. So from now on, I'm just taking questions or suggestions for what to look at next, or troubleshooting if you've been doing it along with me. Someone's asked, can you explain when or why you would correct for reliability as you had in your preprint? And do you recommend doing this, or does it depend on the topic review? It differs in different disciplines. So in the kinds of worlds where I do research, you distinguish between the idea of the relationship between the constructs, that is, irrespective of how well you can measure things, what is the relationship between thing A and thing B? That's the relationship between constructs. Whereas the operational validity is, given that we do measure things with this level of precision, what is the actual relationship between things, or what is the real life prediction with all the measurement error we have likely to be? So it depends on what you want. For any sort of practical, any sort of practical outcome, it probably makes more sense to think about the operational validity. That is, what's the relationship between thing A and thing B, even if they're not measured reliably, and then you don't correct for reliability. But it's a thing, correcting for reliability, because Hunter and Schmidt did it when they first started doing meta-analyses in org psych and business. So it's from that sort of tradition. I can show you how I did it until someone asks me another question. Where are we? So here's positive affect total. Here's the reliability of emotional intelligence. And here's the reliability of positive affect. And to get to the corrected reliability, there's a standard formula, which is this. It's the observed correlation divided by the maximum possible correlation given the reliabilities. That's what it is. And then so I could enter this value for the correlation in instead if I wanted to correct for reliability. It tends to be an organizational psychology / business thing, not a health / medicine thing. So the two most common effect sizes that you would look at would be the difference between groups, either as Hedges D, or Hedges G, or Cohen's D, or the correlation coefficient. But sometimes you also have binary data where you want to predict the risk of something, and there's ways to do that in this sheet. You could also, in this first workbook, enter just an effect size and a standard error. So this might be useful for scenarios in which the methods of measurement of whatever you're interested in are all different. So people are just reporting a whole bunch of different stuff, and you've had to convert it to one sort of effect size. So you can also do that sort of meta-analysis in JASP, but I feel like if you're just starting off, this is like a relatively easy thing to do. Like it's just free software that's basically a bunch of Excel sheets and you paste things in. So I can see that people are going, and I think that's fine. So I'm just going to hang around, I think, and take questions if anybody has them. What are the weights beside the forest plot? So these weights are what proportion of the total sample size. So the weights are proportionate to the sample size. When you're computing a meta-analysis, to get to this value, what you're doing is weighting each estimate by the sample size of that study and then dividing by the total thing. So I can just show you that actually. And that's what the weights are. In a correlational meta-analysis, what you're doing is just weighting the sample size, weighting the effect by the sample size, and then dividing by the total sample size. I'm not quite sure how they adjust it with the different sample sizes of groups here, but that's what it is. And the weights of the sample size, they're like how much of the total sample consisting of these 2, 9, 3, 5 to each of the studies. So this is a really good question that's just been asked in the chat. If I'm looking at the effects of interventions on behaviour, can I include studies that use between subjects designs and those using within subject designs? So this data that I've entered into this sheet, differences between independent groups, in actual fact, some of these are within person and some of these are between person. So people certainly do that. I'm not sure what the best way to do that is. You used R for this, right, Sarah? Do you remember what you did?
That's a very good question. I have to throw my mind back. I think what I ended up doing was testing whether or not there was a difference between the results of studies that were between and studies that were within, and found that there wasn't. So continued with a meta-analysis on that basis. If there was a difference, then I would need to obviously look at subgroup analyses and see what was going on there. But there wasn't a difference for these. That's what I can remember off the top of my head.
So you have to enter it into this workbook and not the other one, because the other one does not allow you to enter numbers that are different if you're trying to, for the two groups, if you're trying to combine within and between group stuff. But it's certainly something that people do all the time, is have research questions that have been looked at both the within person and between person level. Those two different designs.